Hello students, myself Anmol Jain, working as assistant professor in IT department at AKGEC Engineering College. Today I am going to discuss an important topic, that is the register transfer language. That is an important topic, right? So what is the meaning of the register transfer language? As we have the Hindi, English language, or the C, C++ or Java language, and each language has its own syntax, how to write, what should be the structure of the any language. Similarly, we are having the same structure for the register transfer language. That means how the data is going to be transferred, that can be represented by certain symbols, and there is a structure of the statements that we call as the register transfer language. So register transfer language, viewing a computer or any digital system in this way is called the register transfer label. This is because we are focusing on the system's registers, the data transformation in them, and the data transfer between them. Data transformation means that how the data is going to be operated, what operation can be performed on the data, and how it is going to be transferred into new form. Similarly, the data transfer, how the data is going to transfer from one register to another register, or register to bus, or bus to register. Rather than specifying a digital system in words, a special notation is used for the register transfer language. So the purpose of this class is that what is the specific notation to write the register transfer statements, that we call as a register transfer language. For any function of the computer, the register transfer language can be used to describe the sequence of micro operation, right? So my objective is that we can write the number of statements for any operation. For example, I have operation A plus B, right, that the add the contents of the A and B, then we can write the sequence of statements, how the data is going to be transferred into register, and how the addition will perform into ALU. All this can be represented into a sequence of steps, right, and these all steps can be written in the form of register transfer language. Register transfer language, this is a symbolic language. We will use some symbols. This is convenient tool for describing the internal organization of digital computers. So we are using symbols. We will use or we will describe the internal organization of the digital computers. It can also be used to facilitate the design process of digital system. Once we write the statement, we can also analyze the design process of the digital system. Next, the designation of the register. What are the different way to write the registers? How we can designate the registers? So registers are designated by capital letters, sometimes followed by the numbers, right? For example, we can call a register name as A. We can call a register with name R13, R1, R2, R3, like that. Or there are certain registers that we are the standard name, that suppose IR, that we call as the instruction register. Similarly, we are having different type of register that we designate with a specific name. For example, that MAR, that is the memory address register, which holds the address of a memory location, right? So this register is designated as the MAR. Next is the PC, program counter, right? So PC, MAR, IR, these are the standard designated register. How registers can be represented in block diagram? So a register can be viewed as a single entity, and this is represented in a rectangle shape, and in this rectangle shape we can write the name of a register, that is, for example, MAR, memory address register. So this is one of the way to represent a register. Next way of register is designation of register, a register, portion of a register, a bit of a register. So these are the different ways of the register, representation of the register. Suppose this is a register R1, we can use a rectangular box and write R1. That means this is a register R1. Second way of representing of the register is that showing individual bits. Showing individual bits means that this is a register which is having bit 0, bit 1, 2, 3, 4, 5, 6 and 7. So it is having total 0 to 7 bits. That means 8-bit register. This is a 8-bit register. We can also represent like this. Similarly, we can write the register in two parts. That is 0 to 7 bits and 8 to 15 bits. That we call as the program counter low bits, and this is called as the program counter high bits. That is used for the designation of the address. Similarly, we can also write the bits number on the top of the register just to specify the size of the register, and we can write the name of the register in middle of the rectangular box. So this is showing that this is a register R2 which is of size 16-bit. So these are different ways to represent the registers. Next is the register transfer. Register transfer means copying the contents of one register to another. This is a register transfer. We are going to copy, or in general language we say that we are transferring the contents of one register to another register. For example, this is represented by this statement R1 arrow R2. So this is read as, in this case, the contents of register R2 in this contents of register R1 are loaded into R2. And the contents of R1 are going to be transferred into contents of, in the register of R2. So in this case, the contents of register R1 are copied or loaded or transferred into register R2. A simultaneous transfer of all bits from the source R1 to the destination R2 during one clock pulse. That all the bits of register R1 will be transferred into R2. Note that this is a non-destructive, that is, the contents of R not altered by copying them into R2. Important thing is, it is it is transferring, but it is non-destructive. Non-destructive means that the contents of R1 are still in R1. Only a copy of data of R1 is being transferred into R2, right? So if I say that suppose the register R1 contains 0011 and it is being transferred to R2. Now the R2 contains 0011, and what is in R1 now? R1 is still having 0011 because only a copy of data is being transferred to register R2, right? So take care of it. It is used when we solve the numerical problems. A register transfer such as R5, R3, it implies that the digital system has the data lines from the source register R5 to destination register R3. Parallel load the destination register R3 control lines to perform the action. So this is mean that it is going to transfer the contents of R5 into register R3, and it is designated that the data will be transferred through the buses. It is implied in this statement. Next is the control functions. Still we were talking about that the data is going to be transferred from one register to another register, but important thing is when the data should be transferred. I repeat, still we were talking about that the data is transferred from one register to another register, right? But when the data will transfer, so who will control the transfer? So there should be a control function to control the transfer, right? So often actions need only occur if a certain condition is true. That means the data will transfer from one register to another register only and only if a condition is met, if a particular logic is true or if a particular logic is false, only then the transfer will occur. So we need a control function to control the register transfer. So this is similar to an if statement in programming language, right? If this is similar as the if statement as in C, C++ or Java. If a condition is true, then the function will execute, otherwise not. So in digital system, this is often done by a control signal that we call as a control function. If the signal is 1, the action takes place, right? So otherwise not. So this is represented as suppose there is a statement P contents of R1 is going to be transferred into R2, right? So what does it mean? That this P is known as the control function. This P is my control function or control unit. We also call it as a control unit, or sometimes we also call it as a load unit. Load. So these are the different names which we call this function P. This is my P. This is my actual my logic circuit. This is my control function. Only this statement will happen if P equals to 1. That means if it is true, only this transfer will occur. So this is the way to write a register transfer language statement which is having a control function. What does it mean? That control function colon control function followed by colon followed by register transfer, whatever be the statement. So this is the way to write a register transfer language statement with the help of or including the control function, right? Now the important thing is how these control functions are implemented in hardware implementation. So this is related with the hardware implementation of controlled transfer, right? So these questions are asked in paper, that design the hardware implementation of this particular statement or register transfer statement. So we should take care of the following items while we were designing the hardware implementation. Number one, you should be very clear that what is the control function. You should able to read the statement first. What is the control function? So in this statement P, this is my control function or this is my control function. Second, how many registers are required to perform a statement? So number of registers required is R1 and R2. 2 registers are required, right? Next, how we design the control or how we design the hardware implementation of this control transfer. Number one, whatever be the my control function P, we design a block diagram for it. This is my control circuit P. We need 2 registers. We need 2 registers. One is R1 and one is R2. If there is no size decided, then we write that the register R1 and R2 are of the same size. It is implicit, right? And it is going to transfer the n bit of R1 to R2, right? So this is my first register. This is my second register R1 and R2, and the data is going to be transferred from R1 to R2. So we can represent it by the sign arrow, the direction of transfer, that the content of R1 is going to be transferred into R2. So 2 statements still I have done. One is design the control function block, decide the number of registers, design the rectangular box for each register, show the direction of the transfer, from which direction, from which register to which register the data is going to be transferred. Next, now this control function should be connected. Now this control function should be connected to which register, right? So the important thing is the control function is connected through the destination register. Destination means where the data is going to be transferred. Data कहाँ transfer हो रहा है? So in this statement, the data is going to be transferred from register R1 to R2. So which one is the destination register? So R2 is my destination register in this case. So R2 is my destination register. Right? So the control unit will be connected with the destination register R2 only. Right? So this is the next step that is to be taken care of, that the control unit should be connected with destination register. Next point that is to be taken care of, that the clock. Each register must be synchronized with the clock. So what we see here, that this clock is attached with register R2, register R1, and the same clock is connected with this control function. That means control function and the related register must be synchronized with the same clock. So this is the overall process to design the hardware implementation of the control transfer. So here I have written also the same clock control the circuit that generate the control function and the destination register. Registers are assumed to be positive as triggered flip-flop. Next, there may be a possibility that there are two statements that are to be occur simultaneously. So if two or more operations are to be occurred simultaneously, then they are separated with the commas. So if there is a control function P, there is a register transfer R5 to R3, and at the same time the contents of instruction register should be transferred into memory address register, that can be written, but these two statements should be separated by a comma. So two statements can be separated by a comma. So here the control function P equals to 1, load the contents of R5 into R3, and at the same time load the contents of register IR into register MAR. So we can write two statements or more than two statements also if they occur at the same time, and but this should be separated by a comma, right? So these are the overall summary of the register transfer language, that what we symbols we use the capital letters like MAR, R2, these are the examples. We use the parenthesis, it denotes a part of the register, that is R2, that 0 to 7, that is a register R2, its size is 0 to 7 means it is 8-bit register. R2 bracket L, it means it representing the lower side bits. We use an arrow, it denotes the transfer of information, that the contents of R1 is going to be transferred into R2. Colon, it denotes termination of the control function. Whenever we get a colon, it denotes the termination of the control function. Comma, that is used to separate two operations or micro operations like A comma B comma B comma A. So these are the different symbols which we use to write the register transfer. Now we take some examples that how we write or how we design the hardware implementation of register transfer language. So generally these questions are important and asked in the paper, that show the block diagram of hardware that implements the following register transfer statement, and the register transfer statement is by T2 colon contents of R1 is going to be transferred into R2, and the contents of R2 is going to be transferred at R1. So first we should be able to read and understand the statement. So read. So my first question is, what is the control function is this statement? So by T2 is my control function. So this is my control function. This is my control unit by T2. This is my control function. Second question, how many registers are required to implement this statement? So count the number of registers in this statement, R1 and R2, R1 and R2, that means 2 registers are required. 2 registers are required. R1, comma R2, right? So we need 2 registers, 1 control function, right? So how we will design the control function actually? So this is the crux of this problem, that how we will design the control function. So control function is by T2. So simply we have 2 variables for a logic function, that is one is by and second is T2, and they are connected with a AND diagram, sorry, AND logic gate. So here we see that this is by, this is T2, and this is connected with AND gate. So this what this represent now, by T2. So this is my control function now. Second point, what we decided, that we will use 2 registers. I have created 2 registers, R1 and R2. 2 registers R1 and R2. Next, direction of their flow. So register is going to be transfer R1 to R2. So this is one direction. At the same time, contents of R2 are going to be transferred into R1. That means contents of R2 is going to be transferred into R1. So both the statements, data flow has been implemented. Next, I have the control function, that means control unit. Now my question is, now the control function should be attached with, the answer is it should be attached with the destination unit. So which is the destination registers? So in this case, destination registers is R2 as well as R1. Both registers are the destination register. So control unit should be connected with both registers, R1 and R2. Next, the clock. Clock should be synchronized with what? Clock should be synchronized with the registers and the control function. So what are my, this is my clock. This is connected with all the registers, and it should also synchronize with the control function. So in this way, it completes the whole diagram or the hardware implementation of a register transfer. So we should be very clear that first we should be able to understand what the statement says. Second, what is my control function? How can I design with the help of the logic circuit? Second, count the number of registers, implement or show the direction of flow of data. Control function should be attached with which register? So answer should be destination register, or if the destination are more than one, then control function should be attached with all the destination registers. It should be synchronized, and all the clock should be connected with the same register. Same clock should be connected with the register and the control function. Next, sometimes this question is asked. Generally, this question is asked in the university, that they represent the following conditional control statement by 2 register transfer statements with control function. So sometimes it is given that there is a control function that is in the form of a control statement. If P equals to 1, then transfer the contents of R2 into R1. Else if Q equals to 1, then transfer the contents of R3 into R1, right? These are the 2 statements, and implement these 2 statements into register transfer statements. So how can I write? So what are the possibilities of the P and Q? Now we are having 2 logics, P and Q. P and Q. If P equals to 1, then this statement should follow. If Q equals to 1, then R3, R1, transfer of R3 to R1 should be executed. So what are the possibilities of the P and Q? 0, 0, 0, 1, 1, 0 and 1, 1. So what we see here, that this is not a case. That P equals to 0 and Q equals to 0, this is not a case. At least one of them should be 1. One of them should be 1 at a time. So if 0, 1, 1, 0 and 1, 1. So these three statements here, Q equals to 1. If Q equals to 1, then R1, R3 to R1, this statement should be executed. If P equals to 1, then this statement should be executed. If P equals to 1 and Q equals to 1, this is not feasible condition for this statement, because at a time both cannot be the same, right? So this is not a feasible. That means this should not execute and this should not execute. So how can I write these statement with the help of the control function? So first statement, that is, if P equals to 1, then contents of R2 is going to be transferred into R1. No issue, no issue. But if Q equals to 1, then R1 should be transferred into R3. So the Q equals to 1, it depends whether the P equals to 1 or P equals to 0, right? It should be ensure. So how I will ensure that Q equals to 1 at the time P should not disturb it, right? So I create the logic function of P dash Q. When Q equals to 1, then P should be 0, because at a time only one control function should active. So if Q equals to 1, P should be 0, but the value of this function P dash Q, overall value of this function P dash Q should be 1. Q equals to 1, right? Q equals to 0. But how I will make it 1? I will take the complement of this 0, that it makes 1 dot 1, that is overall 1, right? So now this P dash Q will be 1 dot 1, that is, if Q equals to 1, then this statement will execute. Now whatever is the value of P, not whatever the, actually only these two conditions are true. If Q equals to 1, then this is possible case, this is not allowed, right? So in this way we can design two control statement or two functions, that P colon transfer the contents of R2 into R1, second P dash Q R3 to R1. Now if we check all these conditions, if P equals to 1, then this will happen. If Q equals to 1, then this will happen, right? Suppose I say that if P equals to 0, which will happen? This will not happen, right? If P equals to 0 and Q equals to 1, P equals to 0 and Q equals to 1, P equals to 0 and Q equals to 1, then if Q equals to 1, then which statement should follow? Q equals to 1, right? So in this way we have to analyze that what are the possibilities with the help of this truth table, and we can design these statements. Next, draw the block diagram of the hardware that implements that x plus yz, AR equals to AR plus BR. Here we see that this is a control function x plus yz, and these are my register. The name of the registers are AR and BR. So two registers are required, and we have to add these contents of these two registers. So first is x plus yz, this is my control function. So design the control function x plus yz simply, that this is my variable x, y and z. Y and z, they are connected with the AND gate, and the output of this yz is connected with the OR gate, that is becomes the x plus yz, x plus yz, two registers BR and AR, and these two registers are to be added. So we need a n bit binary adder. So the input BR and input of AR is transferred into the adder n bit adder, and the output of this register, this adder is to be stored in register AR. So the output of this adder is transferred into the register AR. Next, the control function should be connected with destination register. So my destination register is the AR. So I have connected the control function with the destination register, that is AR. Next is the clock pulse. Clock pulse should be connected with all the registers. So these are the clock pulse. So these all should be connected, right? So in this way we can design the hardware implementation of the control transfers. Thanks.